you very much. Good afternoon, everybody, and thank you to Sages for letting me present.
You worried you're going to go into arrest, or?
No.
He's in the tracheo tube.
I have props.
Okay.
I have no disclosures. So over the last several years, we've seen incremental but significant development in the world of robot-assisted surgery. However, there are still significant limitations. The existing technology is very large, it's bulky, it's heavy and difficult to move around. It usually uses platform-specific instruments that are not interchangeable between different platforms. The systems right now are also designed in a way that they only perform either a single procedure or a single set of procedures. And finally, telementoring or mentoring itself is really limited because it often requires the institution to buy another console so you can actually get proper mentoring, which can be quite expensive. So realizing these limitations, we really started looking for alternatives, and earlier last year established a collaborative relationship with NASA to explore their humanoid robot called Robonaut for use in surgical space. The core idea behind Robonaut was to develop a humanoid robot that can be in space with astronauts and really work alongside them in a symbiotic relationship, performing tasks that are either too difficult or too dangerous for them to perform, or too mundane for them to be losing their time with. So two things immediately stood out whenever we first met Robonaut. The first one was the form factor, and the second one was the dexterity. Under existing platforms today, what happens is that the patient often gets lost because there's so much technology. But with Robonaut, what we would have would be an assistant surgeon across the table from me, assisting me with a case, actually doing exposure for me using the same instruments that I'm using. But not only that, we would also have the ultimate mentor, guiding me through the procedure, step by step, showing me exactly what to do. So to test this current state of technology on a platform that wasn't specifically built for surgery, we brought Robonaut over to MITE, or Methodist Institute of Technology, Innovation, and Education, and put it through its paces. Here we had a team of physicians led by Drs. Brian Duncan and Dr. Mark Dean, an ENT specialist. And you can see them in these photos wearing gloves, which are used to control Robonaut, and goggles that receive constant streaming video from a Robonaut's head camera. So once we started our experiments, the first limitation that was obvious was the size of Robonaut's hands. Robonaut's hand is a glove size 9. And not only that, but it also lacks a tenar and a hypotenar eminence. And anybody that's used a medical device knows that's vital for a hand to have. So we recreated those by putting foam underneath the glove and then started our first experiment, which was laryngoscopy. And here I want to show you a video of Robonaut attempting to do laryngoscopy. And you can see the limitations of the hand, the design of the hand, and lack of tenar eminence, because the laryngoscope keeps slipping out of its hand. The second limitation that we noted, and you'll see that in a second, is that fine grip that's needed to hold an ET tube. And Robonaut just wasn't able to do that, so it had to palm it. The third limitation was the limited range of motion in the shoulder, elbow, and the wrist, because whenever you're intubating a patient, or a model in this case, you have to bring your forearms together to align all the instruments for a smooth intubation. And here you can see Robonaut really struggling. So moving on to PEG transfer, we noticed very similar problems. Here again, the main limitation was the design of Robonaut's hands. And the lack of the tenar eminence meant that we couldn't use the standard ringed laparoscopic instruments that we usually use, but rather had to get pistol grip ones. And again, we noted the limited supination and pronation and all the limited range of motion in the wrist, elbow, and shoulder again. And you can see here how Robonaut has difficulty supinating and pronating. So of course we asked ourselves the question, we know in a way what the limitations are. So how can we improve Robonaut? How can we get Robonaut to operate? We know we have to change the design of the hand, make it smaller, add a tenar, hypotenar eminence. We know that we need to improve the range of motion, which NASA has already done with the new platform and new software solution that they've implemented. But then there's dexterity. How dexterous is Robonaut? NASA's engineers based the dexterity of Robonaut on Chatkovsky's hand taxonomy. And this is one of the most famous and most used taxonomies in the world. And Robonaut, in its second iteration, which is the one that we used, is able to reproduce 90% of those movements, including knot turning, which is something that we use in pronation, supination, whenever we're doing either open or laparoscopic knot tying. And then also the finger-thumb opposition, which is something that we use whenever we insert ET tubes. So if Robonaut is dexterous, how come it's struggling with these tasks so much? So what we believe is that the existing hand taxonomies do not fully cover the range of motion and all the moves that are necessary to perform basic surgical tasks. So now we're in the process of analyzing and breaking down hand movements during surgical tasks, very basic surgical tasks like knot tying, to really identify whether the existing taxonomies are sufficient or if new moves and hand gestures need to be added. Once we have that, together with the changed design of the hand, with a smaller hand and thenar hypothenar eminence, and the software solution that NASA already developed for the increased range of motion, we believe that we really have the surgical humanoid robot of the future. Thank you very much.